And I am the Director of Industry and Innovation here at the Freedom Center. We are a power systems and power electronics research center headquartered at NC State University. Our research projects span renewable energy integration, electric vehicle technologies, control techniques, microgrids, applications of wide bandgap semiconductors, and traditional power systems analysis. We have extensive lab capabilities, including multiple simulation labs for HIL development, an electronics packaging lab, and a high bay lab for evaluating medium voltage applications up to 15 kV AC input. Together with our industry partners, we are leading the electrification revolution. Hopefully, everyone is familiar with Zoom. We have disabled audio and video for all participants today, but we ask that you use the chat feature to ask questions. Just as a reminder, you can hover your mouse over the Zoom window and the button should appear at the bottom of that window. Click chat, type your question, and we'll answer as many as we can. Note that this webinar is being recorded and will be posted to the YouTube channel for the Department of Electrical and Computer Engineering at NC State as soon as we can get it uploaded. So Freedom conducts some amazing research, but our students and postdocs are even more amazing. So I'm going to turn things over to our presenter today. Fu Hong.
Thank you, Ken. Good morning, everyone. Thank you all for being here. My name is Fu Hongqi. I'm a 5-year PhD student at North Carolina State University. Today, I'm going to discuss about our research work for battery model parameter estimation. This is a joint work with my professor, Dr. Ning Lu, and Dr. Qian Long and Hui Yu. This work has been accepted by a AAA transaction known as Margui. So if you are interested in my presentation, I welcome you to download my paper and take a look for it. Thank you. And my research effort was mainly focused on the microgrid application. A microgrid is a localized grid of different energy source and load. And the microgrid can be operated with when connected to the grid or island from the grid, but no matter in which case, the battery will be the main backup source for the microgrid system. So that's why the modeling for battery system is really important. In today's presentation, I'm going to talk about the motivation and consideration for my research and the methodology for battery modeling and the approach for the model parameterization. I will also show some case study and I will summarize my presentation. Here is the motivation for our research and why we are favored in hardware in the loop simulation. There are two ways to develop different type system for microgrid system. One is called software in the loop or called model in the loop. Generally, for software in the loop simulation, the researcher can design a system or different control scheme in different software and design the control algorithm in any platform or language. For example, we can develop a test feeder on the OpenDSS, and then we can design some VOVAR control algorithm in Python or other control language, something like that. Then this control engine can coordinate different software together to perform the control scheme. The other method is called hardware in the loop simulation. For this method, we still need to develop different model. But the advantage for hardware in the loop simulation is that first, you can coordinate different test systems together automatically. For example, we can develop a distribution feeder model and also some detailed inverter model together. The hardware in the loop system can automatically connect them together and to perform the interaction between different test systems. The second advantage is because everything in hardware in the loop simulation can be run in real time, even faster in real time or slower than real time, so that the model itself can interact with other hardware. The third advantage for hardware in the loop simulation is the implementation of different communication protocol, such as CAN bus, Modbus, and even other protocol. So that's why we put more favor in hardware in the loop simulation. That's why we put more favor in hardware in loop simulation. We try to develop the whole microgrid model in hardware loop simulation and using this model to test different EMS control algorithm or different control framework for this microgrid model. And for the modeling consideration, the first thing we need to consider is the data availability. We are working with a company called Total so that we can know the data sheet for the equipment implement in the field. We also have some field measurement for the battery system, such as the low current, the terminal voltage, the state of charge, the environmental temperature, and also the battery bank temperature, so that we're trying to use the low current and the ambient temperature as the input for the battery model. We'll lay this model to produce simulation result for terminal voltage, state of charge, cell temperature, so that our modeling objective is try to minimize the mismatch between the simulation output and the field measurement. Moreover, because we are doing the hardware loop simulation, we also want the model can capture some dynamics of the battery system, such as the voltage change or the SOC change. So this goes to our battery model. There are two parts of our battery model. The first part is called electrical means branch circuit model. This model is an equivalent circuit-based model, and the function for this equivalent circuit model is threefold. The first one is we are using this equivalent circuit so that we can simulate the terminal voltage for SOC. The second function is we use a coolant counter so that we can estimate the battery state of charge. The third one is we will collect the heat loss over the internal heat loss. In here, we're using PR to represent heat loss, and we will use this internal heat loss to calculate the battery internal cell temperature. Here is our second part for the battery model. We call it thermodynamic branch circuit. The function for this circuit is to calculate the battery cell temperature. We're using an equivalent RC circuit to represent the thermal model. When we calculate the internal heat loss, which is PR from the internal impedance, we're using this RC circuit to calculate cell temperature. And furthermore, we're using this cell temperature, which is T here, to update the state of charge and the internal voltage. This is the connection and the configuration for our battery model. It's which is pretty simple. We revise this model so that we can apply this model to different battery type. We show in the case study. So here is some take-home message for the battery modeling. The first, because we are doing hardware in the loop simulation, and the time step is down to a few microseconds, so that we need the battery model to be simple enough to be executed in the real time. There could be other models such as computational fluid dynamics model, which is based on differential function, but it's too complicated for us to be run in a few microseconds. The second take-home message is we also want the battery model can produce some detailed transient of the model, because the battery model will connect to an inverter and we need to simulate the system dynamics. And this equivalent circuit model can provide us such dynamics. So that's why we choose this equivalent circuit model. And then we go to the model parameterization method. So we first just recap the objective for our model. The objective is we try to minimize the mismatch between the simulation output and the field measurement, so that we just formulate the objective function as the V summation of the difference. The first equation is the F theta. The F theta here represents the mismatch between the simulation output and the field measurement. The simulation output is a function of theta. Theta here represents the battery model parameter, and because model could have multiple parameters, so the theta here represents a 1/n vector. The second part is the weighting factor for different measurement. In our case, we have 3 different measurements, so that we have 3 different weighting factor. The reason why here we submit we require all the weighting factor as one is we try to normalize this mismatch, but in general case there could be any value, but it just represents different effort size for the measurement. The last one is the constraint for the model parameter. Some parameter we have some bound. For example, the capacity for a battery cell should be a positive number. So that's why we put some constraint here for the model parameter. And because the parameter is a 1/n vector, the lower bound and upper bound is also a 1/n vector. This is our objective function formulation. And then we go to the parameter estimation method. We try to propose a hybrid method by combining a heuristic approach and deterministic approach. Here we shows our objective function, and for heuristic approach, they are mainly based on some stochastic approach, so they could have a very good searching efficiency for the whole solution space. However, if the solution space have multiple peak or multiple value, such a heuristic algorithm could need a very long time before you reach to a stable value. So that's why we try to compare this heuristic algorithm with a deterministic algorithm. Deterministic algorithm includes Gaussian-Newton method or Liebenberg-McCready method. They are kind of objective. They are kind of a Jacobi-based method, and such a method is highly depending on the initial value. So that we try to using this heuristic algorithm to provide a good initial point for this deterministic algorithm. And then once this deterministic algorithm find a good local optima, we will just feedback this local optima to the heuristic algorithm and let this heuristic algorithm to search the whole solution space again. And after a couple iteration, hopefully we can find a global optima for the problem we try to formulate. And I will show a step-by-step example in the later slides. For our case, the genetic algorithm is selected as the global searching algorithm. I know in the literature, people are favor with the particle swarm optimization method. But our case, we try to modify the genetic algorithm so that it can have a better searching performance than the particle swarming optimization method. Here is an example for the genetic algorithm. We will create the random specimen in the very beginning. The specimen here represents the parameter set for the battery model. Then we calculate the performance, which will be the objective function for each parameter set. Then we will generate a new parameter set based on the all population, and then we will mutate some of them, and then we will find the best parameter set again. For the local searching, which is a deterministic approach, we're using trust region reflective algorithm. The reason why we choose this method is because the battery parameter is limited by his bound. So for other approaches such as Gaussian-Newton, they are for unconstrained problem. So that's why we can trust only using the trust region approach. Here is our method. So for original objective function, we try to rewrite it as a polynomial equation based on the Taylor expansion. And then you can see, because theta 0 here represents the initial point for the parameter set, and delta, the lower cap delta here represents the update 12 step for each parameter set. So for this quadratic equation, the first term is kind of a fixed number. So as long as we can find the minimum number for the last two terms, we can find the equivalent minimums for this quadratic function and the objective function. For this second term and third term, we formulate the equivalent subproblem, trust region subproblem of the original problem. J matrix here represents the system Jacobi matrix, and H here represents the system Hazen matrix. The C matrix here is the correction matrix, so that we can make sure the summation of these two matrices is reversible, which means it's a positive definite. And here I will show you a step-by-step example for our algorithm. In the very beginning, we define the size of population is 6. That means for genetic algorithm, there are 6 different parameter set for the battery model. And step 1 means we need to generate new population from old population. Here is an example. We first define the fitness function for each parameter set. And because we have the original objective function, we define the fitness function as the reverse of the objective function. So for example, if a parameter set have very good matching performance, the objective function could be a very low number, very small number. So the associated fitness function could be a larger number. We also define the selection possibility for each parameter set based on the fitness function. If a parameter set have a very good match performance, the fitness will be a larger number, so that the selection possibility will be a larger number. So if at the iteration k, we have the population which is calculated by the genetic algorithm and the deterministic algorithm. So that we will calculate the fitness for each parameter set, and based on the selection possibility, we will generate the new population at next iteration. This is the first step for the genetic algorithm. The second step is called mutation. Because we just generate the new population for the genetic algorithm, we calculate the fitness for all of them. As an example showing here, set 5, set 4, and set 1 has the poor performance compared to others. So we'll just pick these 3 parameter set for mutation. For the mutation, we will take the nth parameter as an example, but this mutation scheme will be performed for all parameters. So for this 3 set, we pick the nth parameter. For this parameter, originally he has a lower boundary and upper boundary, and for these 3 set, this parameter we have 3 different values. We pick the minimum value over these 3 value as the lower limit, the maximum value over this 3 value as the upper limit. So we're using this new range and pick a random number within this range to replace the old number. For example, here we'll pick a random number for set 1 and using this new number to replace this old number. The reason why we're doing that is by doing so, the genetic algorithm can have better searching performance, and also we were using the existing knowledge for this parameter because we're just not using the original lower bound and upper bound. We're using the existing value as the new lower bound and upper bound, so that the algorithm can have a higher chance to converge it to a stable value. This is one of our innovative for this paper. The third step is called recombination or crossover. We randomly pick 2 sets. In this case here, we pick set 2 and set 6. And for these 2 sets, for these 2 parameter set, we also pick one parameter. In this case, we still pick the nth parameter. And then by using a random number, we recalculate this parameter for these 2 sets. In this example here, the random number is 0.5. That means we will just calculate the average number for these two values, and using this new value to replace the old value for this parameter and for both sets. This is called crossover or recombination. Finally, we go to step 4. In step 4, we recalculate the fitness function for all population. In previous 3 steps, we have done the mutation and recombination, and after all this process, we calculate the fitness function for all of them. And in our case, if set 3, which has never been touched before, has the best performance, we're using this set 3 as the initial point for deterministic algorithm. So overall, that means for population of a genetic algorithm, this population have 6 different parameter set, and we run the genetic algorithm. We get the best performance parameter set, which is set 3, and we're using this set 3 as the initial point for the local searching algorithm and try to find the local optima. This is the overall process for this hybrid algorithm. And then this is here shows the overall process for the algorithm. So if we finish step 4, we go back to step 1 again and try to generate the new population again for the genetic algorithm. Here is the formulation for the deterministic algorithm. As I mentioned before, we try to using trust regions reflective algorithm, and here is the objective function for this. For the trust region reflective algorithm, there are a couple of constraints here. The first is the calculation for system information, such as Jacobi matrix and Hessian matrix. And the second constraint here is the constraint for the updating step. Delta here represents the update 12 step for each parameter. The capital delta here represents the size of trust region. So this constraint here means the updating step for each parameter should lower than the trust region. D here is a skew factor for the updating step. C here is a correction matrix for the Hessian matrix. But there are one problem for this formulation. As I mentioned before, the parameter for battery model or parameter for other application, they could have some upper limit or lower limit, but our formulation here only consider the limits for the 12 step. We didn't consider the lower bound or upper bound after when we update the parameter. Here is an example. At the top, the slice is still the original ultimate objective function for trust region, and here is an example for the nth parameter. It's pretty close to the upper limit, and we run this trust region algorithm, and we calculate the 12 step for this parameter, and you can see this 12 step is also very close to the upper limit, and we apply this 12 step to the parameter. You can see after ending this 12 step to this parameter, the resulting update parameter is violating the upper limit. So that means this new parameter cannot be accepted by the model. In our case, it's battery model. So we designed 2 reflection schemes for this situation. The first is we were using the boundary value as the new value for this parameter. The second method is we're using a symmetrical value as for the upper boundary as the new value for this parameter. In other case, if the update parameter is violating the lower boundary, we were using the lower boundary or the symmetrical value of the lower boundary as the new value for this parameter. This is what we call our algorithm as trust region reflecting method. By doing so, we can make sure the new parameter can be fit into the model. So here is also some take-home message. So by formulate the model parameterization method, by formulate the model parameterization problem as a data-driven problem, we can estimate model parameter from the data, for example, such as from the field data or from the datasheet data. So now I will try to show some case study with my method. And because my research was focused on the battery, so I will show 3 cases for the battery. The first case was a benchmark case with no parameter. I will compare our algorithm with other algorithms to see the convergence speed and the accuracy of the result. The second case is I will show some result for lithium-ion battery cell with datasheet data, which could be found online. And the third case where we show some result for lead-acid battery bank with field measurement. As mentioned before, we collaborate with a company and they have a physical test bed so that we can have some field measurement. We try to using this field measurement and to tune our battery model. The first case is the benchmark test. For this benchmark test, we got this battery model from MATLAB Simulink. And for this model, they have 4 different parameters, so we can know the true value of parameter. We also set up the range of this parameter and lay our algorithm to search the true value within this range. For this benchmark test, we have designed some test current profile, and for the environmental temperature, we're just using fixed number. This battery model can produce 3 output, which is voltage, SOC, and battery temperature. We're using these three profile as the target profile for our method. We compare our method with three other methods, which is summarized here. So you can see from this 4 figure, because we have 4 parameters, so we have 4 different figures here. The blue line represents our method, so you can see our blue figure can always convert to the true value with lower iteration number. So this means our algorithm can achieve better conversion speed and also can always achieve the accurate number. This table here summarizes the performance of different algorithms. You can see, as I mentioned before, our algorithm always need a fewer number and before you can reach the stable number. And for this first two method, they can always converge to the true value. So that the error here is 0. And for the other two methods, one of them cannot converge to the internal impedance. So that we didn't consider these two methods in the future comparison.
Fuhong,
Yes.
can you just
Yes.
repeat what those acronyms are for the methods on the previous slide?
You mean this one?
Yeah, so GL SEGA, that's the one that you're using, but then what are the others?
Okay, so I just put the name of the algorithm here. So I didn't put a reference here, but just put a name here. So if you can, I think you can find the article based on the name here. So you can see in the literature, most of them are using particle swarming optimization method, but in our case, we're using genetic algorithm method.
And so you mentioned that your particular method with the genetic algorithm reaches a solution faster than the other or in fewer iterations, but is it also just each iteration faster than some of the particle swarm methods?
No, there's no guarantee. I mean, I can show you some information here. You can see this is our method compared to the other method, which is particle swarming. You can see in the very beginning, the particle swarming can achieve better performance, but after a couple iteration, my method is outperformance and then can achieve better performance. So that means ultimately the genetic algorithm could have a better performance for particle swarming, but for each iteration, it's just depending on the algorithm setting and the stochastic method. So it's not guaranteed.
Sure. Okay. Cool. Thank you.
Thank you. So let me just recap this part. So for this table summarizes performance for our algorithm and other algorithm. The convergent iteration represents the time you need until you can converge, but it's just calculate relatively time. It's not the true computational time. The true value means the final value represents the value this algorithm converge into. So you can see the first two algorithms, they always converge into the true value. So that means the error here is 0. But for the other two algorithms, they have very small stable errors. For the second case, we try to compare our method. Compare our method with particle swarming algorithm. And for this test case, we try to apply our method to lithium-ion battery cell, and we got this data from datasheet. It is a constant discharging test, and the discharging current is 32 amp. We also have the arbing temperature data. So our objective is still to minimize the mismatch between the model output and simulation, between the model output and the datasheet data. You can see from this 3 figure, this is the output from our method, and that means you can see the model do very well, and the error between the simulation output and datasheet is pretty small. Here is a figure that shows the summation of the square error. The square error is defined here, and it's calculated when we set all the weighting parameter as when we set all the weighting factor as 1, so we can get such summation for all the matching errors. You can see the original line is the particle swarming particle swarming Gaussian-Newton method, and the blue line is our method. In the very beginning, our method can reduce the matching errors very quickly, and then at this after 40 iteration, both methods have reached a stable value, but our method can achieve lower matching errors compared to the other method. This figure here shows our method can achieve higher accuracy for the model parameter estimation. Here is also a table summarizing performance for these two algorithms. For the first one column, this one represents the square errors of the matching difference. So you can see our method can achieve lower matching errors. For this third case, yes.
Hey, before you go into this example, there's a question from the chat I want to ask you.
Yes.
How does this method account for the varying parameters of the battery as it ages?
We didn't consider the age here because now because in the field we have the data here. Because the data we have here, we don't have any age data, so we cannot consider the age impact into our model.
So for this particular case,
yes.
But if your algorithm is relying on matching field data, then, I mean, you collect the field data, but then you would have to collect more field data to correlate as the battery ages, right?
Yes, that means, for example, we may need to update the parameter every month, because if we're using the battery frequently, the age we can calculate will increase the parameter things. So that we need to update the parameter maybe every couple of times. That's one of the drawbacks for this method, because it's a purely data-driven method. So if we have more data, we can have better performance. And if the chemistry change inside the battery, we need to collect new data for this battery and using this method to estimate a new parameter again. It's possible to consider the aging performance inside the model, but if we try to do that, we need to have a lot of data, which, for example, we need to have 1 year data so that we can consider the aging in the parameter. As I showed you before, the model for the battery we can consider the aging impact into the parameter here. And if we have a very long-term data, such as 1 year data, we can capture such change inside this parameter. But we don't have such long-term data yet, so that's why I didn't consider any agent impact into this model.
Sure. Okay. Thank you.
And for our last case, we collect some data from the actual field tests, and this is for lead-acid battery. So we were using the field measure low current and the ambient temperature as an input for this battery model, and we try to compare the model output of battery voltage, SOC, and ambient temperature. You can see the voltage and the matching for terminal voltage and battery SOC is pretty good, because in our case we try to using our battery model for energy management system. So the SOC estimation is really important for us, and because we're doing hardware loop simulation, the terminal voltage dynamics is really important for us. For the temperature matching, you can see the maximum matching error is around maybe 3 or 4 degrees. In our case, we're only using this temperature as a protection, so that will just put a lower weighting factor for this profile. So that's why you can have a larger errors. Here is again the the summation for the square errors, we can see, as I showed before, there's no guarantee in each iteration our method can outperform other methods. You can see here in the very beginning, the original line, the orange line can achieve lower matching error, but after couple iteration, our method can achieve better performance compared to particle swarming Gauss-Newton. So, and again, this is a table summarizes the performance of our method and the particle swarming Gauss-Newton. So you can see our method is outperforming everywhere. And finally, and with just some take-home message for this algorithm. So again, this algorithm is a hybrid algorithm, so that you can kind of like balance the trade-off between the searching efficiency and accuracy. But also this method is a general method. It can apply to different models, such as generator model or battery inverter models, as long as we can calculate the system Jacobian matrix and Hessian matrix, we can using this method to estimate the model parameter. And this is finally, I will summarize my approach. And so for my presentation, I just talk about our parameter, our model parameter estimation method, which is a hybrid method. This method can achieve good performance for battery model, but if we can have accurate simulation. If we have accurate simulation for battery model, so we can do better study for the microgrid application or battery application. And we also have another paper which is using similar approach for the generator model, and this paper has been submitted to attribute transaction. In the future, we're also working on the model parameter. We're also working on the online parameter estimation using Jacobian matrix and Hessian matrix, but this will be our future work. And then thank you all. I would like to thank you all again for being here. It's a really great honor for me. And I also would like to thank you, Total SA from France, for their support for this work. And I also have some backup slides. The first one will be the equation for the electrical mean circuit. The second will be the equation for the thermodynamic circuit. And the last one will be the process for the trust region algorithm. You can see they're pretty detailed, but I didn't show in here. So if you are interested, I welcome you to ask me any question or just download my paper. So now I'm happy to answer any question from you. Thank you.
Thank you, Fuhong. We do have a couple of questions from the chat, and I'm going to do my best to ask these correctly. This is kind of a two-parter. How is the electrical equivalent diagram incorporated with the generic battery model? I think from one of the earlier slides that you showed.
This one?
Yeah, and so the question is, how is that incorporated into the generic battery model? But then there's a second question. The generic battery model has predefined list of parameters, including internal resistance. And so how are the RNC components computed from the internal resistance value of the generic model?
So it's similar to the case study one. For example, if we know the true value for the battery model, we will try to find this true value for the model. The first thing is, this model is a general model. This model, I got this model from this paper, but this paper developed this model for large battery. So I just revised this battery model so that it can fit with different battery model. And if we know, it's kind of like data-driven model. So if we know the true value for the parameter, and we will just put some random number into this parameter here, and then we will get the simulation output. And then for example, for our method, we just put some random number for this parameter and put this parameter into battery model, and then we calculate the mismatch between the actual number, the actual output from the target profile, and from our simulation result, we can see the difference, and we're using this difference as the updating 12 step to update our model. So hopefully after a couple iterations, we can find the true value for the genetic battery model. Is there an answer to this question? I
think so. There is kind of a follow-up on how do you get the true value?
So for the true value, it's pretty tricky. So that's why I have different test case here. For the first case is a benchmark case. So that means we can know the true value, which is what it is. And for the second and the third case, we will define the true value as the parameter set who can minimize the mismatch between the field measurement and the simulation result. Because for the lead-acid battery and the lithium-ion battery here, it's a physical battery model. We don't know the internal impedance or the internal voltage source, right? So we just define the parameter set which can achieve a better performance as the true value. So this is one of our assumptions for this approach.
Okay, good. So here's a question on your algorithm selection. When you make the comparison with other heuristic methods, and especially PSO types, did you implement these algorithms for comparison? And then what would be the theoretical comparison in terms of formulation that lead to the outperformance of the genetic algorithm based that's proposed? And I think you showed that as part of your results.
This question is a good question, but it's hard to answer. For both genetic algorithm and particle swarming optimization method, both of them are stochastic algorithm. That means they just need to randomly change some number, and hopefully they can achieve a good number. For particle swarming algorithm, they are two methods to change the individual. I remember for this algorithm, the individual is a particle, or is a kind of like anything or something like that. So you can define the updating speed and updating direction, so that you can get this new result for particle swarming algorithm. And the direction, the change direction and change speed, the change of direction and change of speed is stochastic, is depending on stochastic number. So that means as long as you can have a very larger size of this particle, or you can, if you have a really long iteration number, you can always achieve better number. For my genetic algorithm, I just modify the mutation scheme so that you can have a better chance for searching good performance. But anyway, from mathematically, it's really hard to compare these two algorithms. We just play with different setting or different trip for this algorithm so that you can have better performance. It's also possible to apply this mutation scheme to the particle swarming algorithm. So I mean, it's really hard to compare them. For the comparison in the case study, I just implement what it is in the paper. So this is from my paper here. I just implement what it is from this paper so that I can compare I can compare them with my approach. But for the comparison between genetic algorithm and particle swarming algorithm, I didn't do a lot for this part. Is there an answer to this question, Ken?
I think so, yeah. And the question came from Arena at Chios. So Arena, if you could reply in the chat if you need more details, or if that answers your question, let us know. And then there was a question on the benchmark functions. How are those modeled in MATLAB?
The reason why I picked this model is because you can produce can produce this 3 output, which is aligned with our test case. So that's the main reason why I select this module. And the other reason why I need to do this benchmark test is because we can know the true value for it, so that we can compare our algorithm with others. And the third reason for why we choose this battery model is, I think this is the only battery model we can. This is the only battery model we can find from Simulink, and it also can provide some detailed dynamics for the model. So that's why we choose this model. And this model you can find it from Simulink, just searching battery, so you can find it.
And did you, so on your backup slides, do you have the equations for that case study?
For this benchmark, benchmark battery model, we don't have any equation for this battery model here, because it's just a model from Simulink, so I didn't put anything here. The equation here is for our battery model. For example, this one is for the electrical model. We have the equation for the internal voltage, internal impedance, the dynamic circuit, the thermal resistance, the internal heat loss, and the terminal voltage, and also the coolant counter for the SOC. The other one is for the thermodynamic circuit.
Okay. Okay. And there's a question on, if this is part of your PhD program, and I answered yes, that this was part of your research, but you did more than just develop a battery model for your dissertation, correct?
Yes. So I didn't put a figure here. So, I mean, I try to develop an architecture system for the whole power system by using HL simulation, and the device model will be the lower level for this system. You can see this is a figure here. So the lower level will be device or components such as battery, inverter, PV, and generator, something like that. And the first part for this component model will be the model parameter estimation. And the second part about this component model will be the system control algorithm. For my case, I have designed some microgrid energy management algorithm for it. And the third part over this microgrid level will be the distribution level. So we also developed some code simulation for microgrid and distribution feeder. And the third level will be the upper level, the fourth level will be the feeder head. Will be the feeder level control algorithm. In my case, we have designed some VOVA control algorithm. So for my systems, this is actually an architecture system, and the modeling for batteries is just the lower part, lowest level for this architecture system.
Okay. Yeah, very good. I mean, you went through that pretty fast, but and you make it sound easy. But I know that working on all the development for PhD is quite an undertaking. So I'm assuming that this is somebody who's either considering PhD or as an undergraduate wondering about the level of effort. Yeah, so those are most of the questions that we received. And Fuhong, you got several comments in the chat on, thank you for your responses. So yeah, I just want to, tell you that you did a great job, and thank you for this presentation. Remind everybody as well that, if there's more information that you'd like to know about FREEDM's research, there's a lot of information on our website. There's also a place where you can sign up for our periodic newsletter. Terry and I try to get one out every couple of weeks or so, just to provide a summary of the types of work that we're doing and research results like this one. So please visit freedom.ncsu.edu, and that's freedom without the O. Great. Well, thank you all very much. And like we said, Terry, you'll have this recording up on the ECE website pretty soon. So if you do have any more questions.